2 years into this. I guess I hang out with only ML enthusiasts or something. So for me, there's no debate. But okay, so just a bit about myself. I'm actually from a different domain, which maybe that's why I was asked to give this talk. I don't know. So I am a living domain adaptation. But yeah, my background is actually originally in high energy theory and particle physics. And I've worked on a number of topics ranging from quantum gravity and formal theory and supersymmetry to LHC phenomenology and flavor phenomenology. But actually, a fun fact is that some of my first papers were in astronomy and cosmology. So my first two papers were actually on X-ray astronomy. I did a master's degree in Cambridge with Andy Fabian, studying X-ray spectroscopy of AGN. And I also contributed a small part to this Lyman alpha forest SDSS analysis when I was at Princeton. So I do have a little background. I think my main connection here is through machine learning. So I've been an enthusiast since 2018, and it's gradually taken over my research program. So now it's pretty much what I work on. And so I've written 40 papers or so since 2018, applying machine learning to high energy physics, and also now increasingly astronomy and cosmology. I've also helped to organize two data challenges in high energy physics, one on anomaly detection, which we call the LHC Olympics, and a current one that's concluding on fast simulation, building fast surrogate models for Giant 4, so for calorimeter simulations. So my home base is in LHC, but I'm increasingly branching out into Astro and Cosmo. I'm interested in working on stellar streams and mass density measurements using Gaia data, which I'll tell you about today. Doing some work on upsampling cosmological simulations for mock catalogs for Gaia. Also branching out into simulation-based inference. Recently worked on that for pulsar timing arrays. And with some astronomers, colleagues at Rutgers, we've discovered several new ultra-faint dwarf galaxies using DESI legacy survey and Hubble Space Telescope data. So yeah, so my main interest, I think, is in the potential of astro data to answer questions in fundamental physics, like what is the dark matter, or what is the nature of dark energy. And so that's where I'm coming from to this field. Okay, so I think maybe I was asked to give this talk because I'm from a different domain. So how does that work? So this is not the real meaning of technical meaning of domain adaptation for this talk, but I thought I'd just give a few sociological insights when you try to compare high energy physics, mainly LHC, and astro. So the first thing you come to is the nature of the data. So how available is it? So I think in high energy physics, we live in a world where it's basically private, it's closed. You have to be on the experiments to analyze it. And so as a theorist, you don't get to touch the data. So I'm a theorist by training. And so that limits you to, if you want to do ML research, it limits you primarily to proof of concept work, which can also be freeing. So you don't have to worry about too many of the details. You can play around more. Meanwhile, astro data is great because it's mostly open. As we were discussing at lunch, it's not completely open, but compared to LHC, it's like very open. And so that makes it possible to do, complete pipelines. So from proof of concept all the way to data analysis. And that's what I find super exciting about working in the astro domain. The data, nature of the data, the statistics of the data, I think is also an interesting difference. In high energy physics, we're used to every event being independent and identically distributed. So every collision is happening, irrespective of the next collision. And in astro, I think you have different kinds of data. So you have IID data. It depends on how you look at it. So maybe you're interested in the distribution of stars in the Milky Way or the distribution of galaxies. And you can think of them sometimes as IID. Or you have sort of one universe, and that's your data. In which case, you don't get to leverage the statistics of having multiple events, and you're stuck with just that one data point. So that's an interesting and important difference, I think. Now, regarding simulations, I know a lot of people in the room work on simulations, so I hope you won't be offended. But I think for LHC, we understand the standard model extremely well, and we've developed a suite of simulations through many decades of effort. So now they're extremely cheap and extremely accurate, I would say. They're still not accurate enough for the precision requirements that we have, which I'll get to in a moment. But yeah, they're very cheap and accurate. Compared to in Astro, I think the simulations tend to be rather expensive. And we're still finding out about their accuracy. So I think so that's reflected often in the nature of the training data that we get to use in these two different fields. In high energy physics, we're used to training on millions or tens of millions, hundreds of millions of events. So we're not limited by training statistics usually. Whereas in a lot of the Astro papers, I'll see, we trained it on 1,000 instances or, 10,000 instances. So the size of the training data is often a lot smaller. Now we come to precision requirements. I think in high energy physics, these are very extreme. So, we need agreement between theory and data over many orders of magnitude. You need 5 sigma for discovery. The stakes are very high. We're adding a term to the fundamental Lagrangian of nature, yada, yada. So precision requirements tend to be rather extreme. In Astro, I think you can be less extreme with the precision requirements. Also, you don't understand necessarily the initial conditions. You don't have complete control over the system. So yeah, so I think the precision requirements are less, and that actually makes life easier for doing a lot of ML research. And finally, I think here's an interesting sociological difference between high energy physics and Astro is discovery. So I think in high energy physics, people are terrified of making a mistake and being wrong. And so it's very fraught. You're discovering a new particle or something. So we really need 5 sigma. We've gotten used to that standard. Whereas in Astro, you can discover candidates, and that's okay if you're wrong. I think. Correct me if I'm wrong. But people are less uptight about things, which I think is great. And you can always, you're not discovering a fundamental term in the Lagrangian. It's just another weird object in the sky. And you can always follow up with more observations, whereas maybe we're stuck with the LHC for our lifetime. So we're kind of stuck with the data we have. So I think that's very refreshing. Okay, so those are my sociological comments. So probably what I'm going to give you now, getting more into the technical stuff, is a very idiosyncratic review. I am not an expert on the Astro literature. After I made sure this was not a mistake to ask me to give this talk, I said yes, because I thought, well, this is a good opportunity to learn about this topic. So I'm going to share that with you, and I hope you get something out of it. I certainly learned a lot preparing this talk. And yeah, so sorry if I don't highlight your work. It's not because it wasn't important, just because I'm ignorant. Okay. So also last thing is, like, an hour is a very long time. So please feel free to shout out any comments, interrupt me with questions, anything as we go along. So yeah. Okay. So what is domain adaptation for real? So I think this was a nice thing I found online that kind of gets at the heart of it as far as what it means, as far as, yeah, what I would say it means, is that in general, we want our machine learning algorithms to learn general robust concepts and apply them across different domains. So a human, having lived a long and experienced life, I guess, understands the concept of sleeping and sees these pictures. If we trained on just people pictures or people experiences, we'd still hopefully recognize that whatever that is, a donkey or something, is running. Maybe we've never seen a donkey before, but we can interpolate, or actually I think it's more like extrapolation. So people say machine learning methods have trouble extrapolating, but actually I would view domain adaptation as a form, maybe hopefully a controlled form of extrapolation. So we're trying to extrapolate from the data we train on to the data we test on, which might not be the same thing. And it's controlled because we do techniques that still expose us to the target data, which has less information about it, which we have less control over, but we expose ourselves to the target data in such a way that it's not just a totally blind extrapolation. Okay, so the reason we need domain adaptation, the reason this is important is that, so in many cases, the training data, so the source, which we're going to refer to as the source, or S, the training data for machine learning methods are often systematically different from the deployment data, which we're going to call the target, or the T. So if you optimize, so a classic example of that is when the source data, is simulation, and you need that simulation because the simulation comes with ground truth labels, and say you're training some classifier or regression method, so you need to train it on something that has labels. So you resort to simulation. But of course, the simulation could be different than the real data, and in general it is. And so, and the target data T, so it's different than the simulation. Also, it has unknown labels. So maybe it doesn't even have the correct, label proportions that you trained on. So if you train on the source and evaluate on the target, and they're very different, or even a little bit different, that can lead to major degradation in the performance. It could lead to really wrong results. If you're doing a measurement, it can lead to, an uncontrolled bias or incomplete coverage of the uncertainties. So you could really get the wrong answer. So that's why we need techniques to basically mitigate this difference between training and deployment data. Okay, so two common situations are, as I already said, model misspecification. So that's where the simulation and data have systematic differences. These are two examples from the literature. So one of them here is a recent paper by, I think there was a talk about it today. Yes. So so it's weird for me to explain somebody else's work who's probably in the room. But anyway, so where so some regression method was trained on one suite of subgrid physics of cosmological simulations, and then evaluated on another one, and you could see the systematic bias. So if you wanted to infer, if you trained it on this simulation and that was your data, and you wanted to infer omega matter from the data, you'd probably get a biased result if you did that. So this is another recent work exploring simulation-based inference and what happens if your data has out of distribution measurement uncertainties, which lead to sort of out of distribution data or uncertainties relative to your training data. And that can lead to extremely biased results as well, as shown in orange. So this is a paper by Alexandra showing another kind of domain adaptation, more like data to data, I would say, where maybe your data is changing with time, like an earlier version of the survey had more noise than a later version, or something got corrupted in the survey, in the data, in instrument. So this is showing, for instance, if you increase the noise or increase the an adversarial attack in just a single pixel, you can change the classification of a galaxy morphology from the correct one to an incorrect one without any, if you don't do any domain adaptation techniques. So yeah, so either model misspecification or changing data, both of those are important use cases for domain adaptation. Okay, so just a word about the broader context. So I think there's a broader context of what's called transfer learning that domain adaptation fits into. So transfer learning, it's very popular in many applications these days with foundation models. But the idea is that it's even more ambitious, I guess. It's that you could potentially train your machine learning method with some set of tasks on some training data, and you could evaluate them on a completely different task or a completely different data space. So maybe you train it on images and you evaluate it on text or something like that. I don't know. So domain adaptation, I think, which is more the focus of this review, is sort of a narrower task where the data lives in the same space between the source and the target data sets, and generally you're interested in the same task. Okay, so it's a simpler, but still very important set of techniques. Okay, is there a question? Okay. Good. Oh, and one more thing about that. So transfer learning, although it's, I think, a broader concept, has a standard technique that we've all heard about, where you pre-train often on a bigger data set, and then you fine-tune on a smaller data set, maybe with less labels or something. And that general technique also finds a place or has an application to domain adaptation. So this could be a special case of that, and techniques that do this could also do that. Okay. So good. So here's another thing that I did. I went to ADS and I wanted to get a lay of the land for domain adaptation in astronomy. So I did the following search for these terms. Also, to get rid of some spurious results, I put in machine learning. And I think I restricted it to just a smaller subset of publications. So not every possible journal. And so this is to get rid of some other noise. And this is what I found. So there's been about 350 papers on this topic. And starting sort of in 2014 or so. And you could see actually, so if you, so ADS has this nice visualization tool. You can group papers by a network, I guess citation network. So this purple one, I think, which is the biggest category, is like a miscellaneous. It didn't know what to do with those. They're not all about solar physics. So yeah, but the other ones are actually pretty meaningful. So there's been a lot of work on galaxy morphology, stellar spectra and photometric inferring things from photometry, gravitational waves, and gravitational lensing, and radio astronomy. And you can also see as a function of time, if you ignore the purple one, that the earliest papers were on stellar photometry, doing domain adaptation for that. And then sort of in 2017, there were galaxy morphology papers starting to happen, and also gravitational waves. I guess that coincides with LIGO and their discoveries, probably. And then recently, I think gravitational lensing seems to be taking off. So yeah. What I also found interesting was if you did a additional search for what kinds of machine learning tasks domain adaptation is being applied to, the vast majority seem to be about classification and regression. And that's also going to end up being the focus of this talk. A decent fraction are starting to talk about generative modeling, so domain adaptation for that. I guess let's say you train your generative model on simulations, and then you want to know how well that those features reproduce the data. And then actually very few papers talk about simulation-based inference. So that was one thing I learned just by doing this exercise. So that's actually I think an interesting frontier for domain adaptation research is to SBI. It's also like a much harder problem, I think. So yeah. Okay, so you might also be interested to know that the machine learning people have been doing domain adaptation since maybe before some of us were born. So it's actually a very old topic, predates neural networks and all these things. So it's a general problem that they've developed techniques and categorizations and understanding for. And yeah, so the context is usually, as we said, so the source and the target domain have different distributions, but the same space, yeah? And often they'll divide things up into sort of inputs or covariates, X, and outputs or labels, Y. So that's an interesting, that's a useful distinction to draw. And then there's many different types of domain shift. It's actually an active area of research and application is to identify what kind of domain shift your data has. But so this is not a complete list, but one of the most oldest and most popular kinds of domain shift is what they call covariate shift, where the X distribution, so distribution of inputs, are different between source and target, but the class probabilities or the posteriors of the labels are the same. Okay, So that takes some getting used to thinking about that. What does that mean? So it turns out what that means is, well, it's maybe not always the case, but it's commonly caused by if you have a selection bias or some kind of efficiency in your data taking that depends primarily or only on the input variables X and not directly on the labels Y. So for instance, maybe your survey has a, so actually, yeah, one common, actually, I'll give you an example in a little bit, but I can mention it now. So you might have a survey that has photometric data and spectroscopic data. And the spectroscopic version of that survey is heavily biased towards brighter objects. So that is a version of covariate shift, where the bias in the data set, affects how the is caused or affects is caused entirely by the brightness of the object, and then doesn't affect other labels, other outputs that come out of inferring things from those objects. Okay, so another common kind of domain shift is something called label shift, which is basically the same as covariance shift, but you switch what's the same and what's not the same. Okay, so in that case, the distributions of the labels are different, but the distributions of the covariates for each label, so think of it like binary classification. You have a distribution of cat images and a distribution of dog images, and those are the same, but the class weights are different. So in the source data set, you might have 90% cats, and in the target data set, you might have 10% cats. So that would be an example of label shift. So it's often caused by class imbalance. It also has interesting connections to what we would call weakly supervised techniques. So weakly supervised anomaly detection, which we've applied in high energy physics and also now in astro to search for stellar streams, which I'll tell you more about later. And in the ML world, I actually recently learned that they've been working on this for decades, and it has a name called positive unlabeled learning. So if one data set has only positive examples and the other data set has a mixture of positive and negative examples, but you don't know what the mixture is, you can, as long as it's described by this label shift, you can use weak supervision to figure out the proportions and which events are positive and which are negative. Okay, so the last category that's commonly talked about is something called concept shift, where the covariate distributions are actually the same, but the posterior probabilities are different, or vice versa. And so what does this mean as far as we're concerned? So I think what this means is that the source and the target inputs, they look the same, but the labels actually mean something different in each case. And so if you think about this some more, I think this is the most common scenario for pretty much all of the scientific applications. Well, so selection bias is a thing too, but this is a common sim to real or simulation data discrepancy situation. So basically, we could ensure that we simulate the same distribution of all the inputs, fine, but maybe we just don't understand the categories, So we can make sure all the pixel distributions look the same as the real data, but we don't understand, or we're not simulating properly what an elliptical galaxy is or something. So if you're not simulating each class correctly, but you can still ensure that the data looks like what the real data is in terms of the inputs, that's a typical, I think, simulation or model misspecification scenario. Scenario. Okay, so good. So now I'd like to tell you about some of the various techniques that people have come up with for dealing with domain adaptation. And there's no one-size-fits-all approach. And in fact, which kind of domain adaptation you have often dictates what kind of technique you should be using. Okay, so the first kind of technique is actually one of the oldest ones. It's called importance reweighting. And actually, I didn't find too many examples of this in the astro literature, but it's the standard thing you do when you have covariate shift. And the idea is that you've trained, if you want to train on something that looks like the target data, okay, but all you have is the source data, then you can, ideally, you could reweight the source data to look like the target data using importance weighting. But these weights generally, should depend on both the inputs and the labels. But in the target data, you don't have access to the labels. So how do you do this reweighting? And that's where you use the covariate shift assumption, and you can show that the dependence on the labels actually drops out. So then you can learn a reweighting just in terms of the inputs. And so you can get this to work. Okay, and there's many techniques for learning this importance weight. And so one trick you can do is, for instance, train a binary classifier between target and source input features. And if that classifier is close to optimal, it'll approximate these importance weights pretty well. Okay, good. So I was able to find some examples of importance weighting in Astro. Actually, one of the earliest papers on domain adaptation from 2016 used importance reweighting to basically go from, so this is what I was saying, so to go from SDSS galaxies that have spectroscopic redshifts and photometry. So the goal is the task is to predict redshift from just photometry, so photo Z, and you train it on a labeled data set where the redshifts come from spectroscopy. And then you want to apply it to the target data set, which is all of SDSS with photometry only, which is a much bigger data set. So this is an example of covariate shift, as I was saying, because the spectroscopic galaxies are heavily biased towards brighter magnitudes, as shown here. But once you account for that brightness bias, you expect that the redshift inference doesn't depend on whether it was in the source data or the target data. So yeah, so that's the assumption of covariate shift. And so yeah, what they showed is if you do this importance reweighting, you can basically, so this is showing the performance of the regression task for various approaches with and without domain shift, with and without this importance weighting. And on the far right, you could see a much lower loss, a much better performance on that task if you do the reweighting as expected. So yeah, so that's an early example of this reweighting technique. I actually found some interesting papers more recently, a bit more recently, proposing alternatives to reweighting. So it turns out that, so if anyone's ever used importance weights before, you may know that they can be numerically unstable and have very high variance. In particular, if your data has regions where the source or the target don't overlap, these weights can be basically useless. And so what these people found or claimed to find is that instead of directly reweighting, you can actually use something called the balancing property of importance weights, which is they're also called propensity scores in causal inference. And you can show actually that if you condition on these importance weights, the distributions of the covariates become the same. You can also account for the difference between target and source if you basically bin your data in the importance weight. So you basically create strata of the importance weight. And so they show that if you train your machine learning methods in these strata, you can do the same or better as directly reweighting. So that's what's shown here, comparing IPS, I think, is importance weights, and you get a much better domain adaptation. So going up and to the left is better. You get a much better domain adaptation on photometric classification of supernova, for instance, or this is the same photo Z problem here, doing this stratified approach. So yeah. Okay, but actually there aren't that many papers doing any kind of importance weighting or covariate shift that I found in astronomy. So a much more active area seems to be a different approach, which is, I would call, coming up with features that are try to be invariant or the same, have the same distribution between the source and the target. So the idea here is to add some kind of penalty term or regularizer during the training of your machine learning method that actively tries to penalize any difference between distributions of learned features in the source and target domains. So this diagram is illustrating the general idea. So your source has labels and has inputs, and let's say you're trying to train a classifier. So you usually you could break up your neural network, CNN or whatever, into two parts and call the first part a feature extractor, and the later part the actual classifier. And if you do that, then so this part has trainable weights and that part has trainable weights. And so you imagine feeding the source data through the feature extractor, extracts some features F, and that by itself would be the classifier, is some loss function calculated using the extracted features and the labels. And that by itself would be undomain adapted. Meanwhile, you have target data, which you just have the inputs and you don't know the labels. You can also pass that through the same feature extractor. And then you have some domain penalty that sees both the source features and the target features and tries to penalize you if those two are different. And that can come with a hyperparameter lambda. So if you crank up lambda, you get extremely good domain adaptation, but possibly at the cost of a very suboptimal classifier. And if you have small lambda, you have the opposite trade-off. Okay, so that's the general approach of trying to improve the problem of domain adaptation or mitigate it during the training using a regularizer term. And there are two approaches that have been explored. A lot of the work that Alexandra did, I think, is pioneering the application of these approaches in Astro. And so you can classify the two different main approaches into adversarial approaches and distance-based approaches. So in the adversarial framework, you actually write down a second, so the domain penalty is actually a second network, which acts like a discriminator in a GAN, and aims to distinguish the source distribution from the target distribution. And just like a GAN, this has to be trained with a min-max objective, which has its downsides in that it can be unstable to train. But yeah, so the idea is if these two have the same distribution, then the discriminator can't tell them apart and returns a random output. Whereas if they have a different distribution, the discriminator can tell them apart. Okay. The other kind of domain penalty is distance-based and is convex instead of min-max. And so if you can come up with a measure of distance between distributions that's easily calculable from samples, you can plug that into your training and use that directly as a regularizer term. And so a popular choice that from the ML literature has been applied successfully to Astro data is this maximum mean discrepancy. It can be calculated from samples using this formula. So basically this MMD estimated with samples is 0 if these two distributions are the same, and otherwise it grows the more different they are. So it's sort of like a Wasserstein distance between distributions. Okay. Somebody should stop me. I've been talking for a while. Everyone sleepy after lunch? Okay. So, all right. So there's actually an interesting connection between these techniques and high-energy physics. So interestingly, we've been using both distance-based and adversarial techniques, but for a slightly different problem. Not to say that domain adaptation isn't an issue for us, it is, and we probably should be doing these techniques, but I haven't seen them in our literature. So instead, we've been using them for a different, slightly different problem, which is decorrelation. So there, the question is, or the thing we're trying to solve is we have some machine learning output like a classifier, and we want it to be independent, statistically speaking, of some protected feature, which for us is usually actually continuous, some kind of mass or something. And so statistically, we want the neural network output and the protected feature, their joint distribution, to factorize. And actually, so you can think of all the domain adaptation as decorrelation in a binary label. So if this mass is a binary label for 0 being source or 1 being the target, decorrelation actually reduces to domain invariance. So yeah, so they're actually the same thing. But yeah, for us, usually we're interested in decorrelating against a continuous parameter. And actually, you can show that, so the statisticians have shown already that the MMD is something they also called energy distance, and there's a continuous analog of that, which they came up with called distance correlation. And we first applied that to decorrelate a machine learning method in the context of high energy physics for something called top tagging, or identifying boosted top quarks in this paper. And then for the adversary, if you apply it to a continuous output, this was referred to as learning to pivot, or coming up with pivotal variables in this work. That's with Kyle Cramner and his collaborators. So yeah, so there's interesting analogs of these techniques in high energy physics as well. All right, so some examples in astronomy where these domain invariant features have been used. So I think, so the first paper I found was from 2021 by Alex and company, using it to classify galaxy mergers, where the source were simulated SDSS images from some illustrious simulation, and the target were actual SDSS images. And they explored so here's a plot showing, if they, on the raw, simulation, the performance is very good, but then it drops to that without domain adaptation, and then exploring different techniques, including MMD and adversaries, recovers at least some of that performance. I guess the best is this yellow one, I think. So yeah, that's with domain adaptation, with the adversary, I think. Yeah, and then it's been subsequently picked up for a number of other applications, like classifying dark matter substructure in strong lensing images, classifying galaxy morphology, doing cosmological parameter inference, which we heard about today. Yeah, so I think those are the papers that I was able to find employing these techniques, but maybe there are others. Okay, I can also mention one thing that people have worried about in high energy, which maybe should also be aware of. Often you want to quantify the systematic uncertainty you're incurring from doing a simulation by doing 2 different simulations and comparing them both to the data. So we would call that a 2-point uncertainty. And if you look at 2 different simulations, so I've adapted a figure from this paper that talks about this issue to the AstroCosmo audience. So let's say you have 2 simulations of subgrid physics for cosmological simulations, and you think that they're both different from nature, so you quantify a 2-point uncertainty between them, and that's your systematic uncertainty relative to the data of using simulation in the first place. If you now train some kind of method that decorrelates the difference explicitly between these 2 simulations, which people have tried to do in high energy for analogous things, you might think that you're reducing your systematic uncertainty. I mean, you technically are. The 2-point uncertainty is smaller, but that 2-point uncertainty is not the real systematic uncertainty. It's just a proxy for some much more complicated theory uncertainty that you can't, otherwise quantify. So decorrelating against the difference between these 2 simulations would probably blind you to the underlying true theory uncertainty, which you might, you could see that if you then tried out a 3rd simulation or a 4th simulation, et cetera, et cetera. So yeah, so that's one issue to possibly be aware of. Another issue I think is maybe important to keep in mind is that, in order for these decorrelation techniques to work, they promote that the source and target distributions are the same in terms of the inputs, but this really only makes sense, I think, or works best if the classes between the source and the target domains are similarly balanced. If the classes are imbalanced, then promoting that these two marginals are the same would probably get you the wrong answer. What you really want are the joint with the labels to be the same between source and target, and this is just a proxy for that. So if the classes in the source and target domains are imbalanced, you're gonna get a suboptimal result. And you can't count on the target domain having the same class weights or proportions as the source domain, since it's unlabeled by definition. So yeah, so what we need, I think, are more robust methods to account for unbalanced classes, or maybe the target domain has extra classes or is missing some classes. So there's lots of things that could happen. In principle, if you really say you don't know hardly anything about the target domain. So I think there's actually very interesting recent work using self-supervised contrastive methods that try to classify, use the labels in the source domain to classify them, train the classifier that you want, but also try to align the data in the source domain, in the target domain, try to align that with the labeled classes in the source domain in a self-supervised way, using similarity measures. And that seemed to work quite well. This was demonstrated here, going from one survey to another survey, where the class proportions and of galaxy classification, where the class proportions and even the number of classes were not the same. So we also heard a bit about that, I think, in the debate from Alexandra. Okay, so I think that's a very promising and exciting direction. That's probably, so leveraging the power of self-supervised methods in contrastive learning is probably the way to go for this kind of techniques. Okay. Anybody have any questions or thoughts? No? All right, so that brings me to the fourth thing, which is transfer learning. So as I said, I think transfer learning is a more general problem, but you can certainly take the general technique of pre-training and then fine-tuning and apply it to get good results for domain adaptation. So of those 300 or so papers that mention transfer learning, it was the majority of papers were about transfer learning, actually. I think the majority of those are pretty straightforward. So taking pre-trained image classifiers, often pre-trained on ImageNet or something, and fine-tuning them on Astro data where there's only a small number of labeled instances. So that's proven to be fruitful and effective. Now we're starting to see, I think, some interesting work in the direction of foundation models. And so this was a recent work by radio astronomy people showing how if you trained a foundation model, so using those kind of techniques on a large survey called MirrorBest, and then fine-tuned it on a smaller survey called MIGHTY, you could actually do better than if you just trained on the smaller survey. So that we've seen many examples of in ML now, and I think this is maybe the first example in astronomy where that's the case. So this is a case where you actually really benefit from training on the larger data set, learning a good feature representation, and then fine-tuning it on the smaller one. So you could transfer your knowledge from one domain to another. This one I'm not sure is as, I hope the author's not here, I'm not sure is the same, in the same spirit, but they also talk about domain adaptation in the abstract. So they trained a large language model. Well, they took a large language model that had been trained, Llama 2, 7 billion parameters, and fine-tuned it on Astro PH. Okay, and they found that also led to good domain adaptation or transfer of the knowledge from the full large language model to Astro language. They could ask it questions about the papers, it could summarize them, et cetera, et cetera. So yeah. Okay, that's all I want to say about large language models. So as I said, simulation-based inference, I think, is an interesting frontier for domain adaptation. So I think there's two ways to use SBI that you could think of. So one is to speed things up. So, and in that case, so maybe your simulations are already based on some state-of-the-art or so maybe your simulations are already based on a tractable likelihood model, and you're already using that likelihood model to do inference. So maybe that's already the state-of-the-art. I think that's the case, for instance, in gravitational wave interferometry and pulsar timing arrays. They have basically a Gaussian process model that they already use to infer the parameters of the gravitational waves, but it's just extremely slow to do the inference. And so then I think you're doing no harm, at least if you apply SBI to speed things up. Maybe the model is misspecified, but the results you're going to get are no worse in principle than the thing they're already doing. Okay, so improving the model is a separate problem then. You're not doing SBI is not going to lead to more model misspecification. I hope that makes sense. Okay, but I think if the simulations and the likelihood are intractable, you're using more information than is currently done in that field. Like you're doing full field, whereas people are only doing summary statistics like 2-point functions. Then there could be major issues with model misspecification. And yeah, I think it's a very hard problem. So already, domain adaptation for inference is much harder than for classification. So if you're just going for performance, like a better ROC curve, that's much easier, I think, than if you want to get, an unbiased estimator with good coverage of the uncertainties, and having the wrong model that you trained on could really lead you to be way off the mark. So it's a more nebulous thing, I think, than just a ROC curve. And I think it's especially challenging in a lot of astro and cosmology contexts where you're doing SBI with a single data point, right? Like the universe. You plug in the sky map. And so you don't get to, a lot of these techniques that I talked about, they rely on you having a sample of data, of IID data. So none of those things seem like they would work in the case where you just have one data point. Now, a lot of domain shifts are being attempted to be being taken into account in SBI using nuisance parameters. So we've seen talks about that. But what if the error model is wrong? So there could be model misspecification at the level of the error model as well. So these are all things I think that really are going to be important as you try to deploy these things to data. So this was an interesting recent paper I found in the machine learning literature that claims to be able to learn robust summaries. So similar to this feature invariant learning that I talked about before in the SBI context, where, I mean, they did something which I don't think should work, but they claim that it does. So it'd be interesting to look into this more. Or if anyone's looked into this paper, I'd love to talk to you about it, where they are aware that you might apply SBI to a single data point, and they do an MMD-like loss between the source data, which has many data points. Think about all your simulated galaxies or simulated hydrodynamical volumes. That's the X there. And then they want the MMD between that and the single target data point, which is the actual data, the universe. And that's the penalty they put in there. And they claim that that actually works well in mitigating the model misspecification. So I'm kind of skeptical of that, but be interesting to understand that better. Okay, good. So I guess in my remaining time, I'd like to talk about what's actually my favorite topic. So I could pause here for questions. So this was all really the standard domain adaptation stuff that I just took you through. If anybody's still awake. Yes.
I guess I have a very brief question on this paper. So were they using the one data point and the MMD loss during training somehow or afterwards?
Yeah, during training of the, so I think here they're interested in a version of neural posterior estimation where you're learning, first you send the raw data to a compressed representation using like an embedding network. I think they want to, at that stage, that's like the feature extractor, and they want to learn a robust summary. And they literally, I think, so that's I think the embedding network is ADA. And so they literally want that to be the same between the MMD of that between the training data and the source and the target data, but the target data is just a single data point.
Oh, that's really interesting because we've been trying the similar thing and seeing and testing can we reduce the target data set
Yeah.
by a lot? And if you reduce it to something small, usually the MMD doesn't work anymore.
Mm.
But it was like a regular neural net, so maybe the choice of the network here helped.
Yeah, I think this paper was using flows.
Oh,
But
cool.
yeah.
Cool. Thanks.
Yeah. Yeah. Question in the back.
Um, I see domain adaptation being being a pretty effective tool for accounting for selection bias and model misspecification and kind of sweeping it under the rug for future downstream tasks that you want to do. And I can see how for select classification problems, it could be very effective. But in the case of like simulation-based inference, and especially for physics purposes, wouldn't we always want to try to increase the flexibility of our model and error models rather than including whatever strong assumptions that go with the domain adaptation in our inference?
Yeah, so good. So I think so that's probably the third bullet point here about, can we account for all the differences between all the model misspecification with nuisance parameters with an error model. Of course, yeah, that should be the goal. But maybe we still can't completely succeed, in which case maybe we need to get that last extra mile or something. We need some additional techniques. So that's how the role I would see anything like domain adaptation playing here. Also, you might say, yeah, so in the end, you're going to get some inference here using your SPI or whatever, which has a central value and an uncertainty to it. So maybe domain adaptation, so maybe accounting for nuisance parameters or blowing up our uncertainties, we can get good coverage. Maybe domain adaptation can reduce the uncertainties or reduce the bias of the central value. So I think some combination of these techniques would probably be a good idea. Yeah.
I just do want to comment that we have 8 more minutes. I don't know if you have a lot in the next.
I could stop whenever, Yeah. Okay.
So whatever you prefer, and we just want to have a little bit more time for discussion.
Good. Okay. So yeah, I could go quickly through this stuff. So I think this is maybe because it's also kind of orthogonal to the spirit. I think it's kind of trivial to say, there's no problem with domain shift if your analysis is fully data driven. Right? So if you can find a way to train and test on the same data, and if you need labels, that means somehow coming up with labels with the data itself, then you ameliorate or get rid of the problem of domain shift and domain adaptation. So I think it's, you can't always do this, but when you can, it's great. So you can actually, so I've heard it said, you have to have a model, you have to have a simulation in order to infer something from the data, because otherwise, what are you learning? So actually, I think there's plenty of examples where you don't really need a simulation. You can go straight from the data to the inference. So again, you can't always do that, but when you can, it's great. So some examples, I think, of fully data-driven analysis I came up with here. So one of them is, if you deblend galaxy images, if that's what you're interested in, you could create an artificial training set using simulations of blended galaxies, or you could take real galaxies that are not blended and blend them together artificially. And so that's sort of a data-driven technique, I think, which I found nice to see, that should at least get rid of a lot of the problems with with simulations. Another thing is, using autoencoders, like as we heard about in the debate, for learning about the data, interpretability, classification. All of that is data-driven, right? Doesn't use any simulation. And maybe in my remaining time, then I'll just focus on 2 of the things we've been doing that have attempted to be model-free and fully data-driven. One thing I think is interesting to think about, which I don't have any thoughts about, but is something I'm interested in, is whether there's any overarching principles or themes for data-driven analysis, or is each data-driven analysis sort of its own, artisanal ad hoc thing? So we've been doing a number of different data-driven analyses, and I've been searching for some kind of principle that would, tell me how to do the next one. But yeah, so far I haven't come up with anything. Okay, so let me just skip over that. So I think in the remaining time, I only have time to talk about this project very briefly. This is work that we've been doing at Rutgers, led by our very excellent postdoc, Sung Hak, who happens to be on the job market right now. So please take a look at his application. He's got a background both in high energy physics and in astro. So what we're interested in doing is using Gaia data to measure the local dark matter density. And previous approaches to that include rotation curves, using Jean's equation, and all these previous approaches make many model dependent assumptions, like they fit it to a simple parametric model, they impose various symmetries, they also bin the data, which is a simplification that they have to make. Some of them get very precise results, like some of these have no error bars on that summary plot, as far as I could tell, but they might not be accurate. They can't all be correct, that's for sure. And so what we were interested in is whether we could measure the local dark matter density in a more data-driven and model-free way. And so what we came up with, building on previous work by these authors, is a technique that uses the Boltzmann equation. And so if you can first start with a complete and unbiased or reasonably unbiased sample of tracer stars that have full 6D kinematics, which Gaia lets you do, then modern machine learning, in particular normalizing flows, give us access to the full unbinned phase space density, so P of X and V. So we can train a normalizing flow if we have this data and learn this phase space density. Then using the Boltzmann equation, if you assume dynamical equilibrium, which maybe is an okay assumption in some parts of the galaxy, at least, maybe to within 10% or something. But anyway, if you assume that, then the rest of the Boltzmann equation gives you access to the acceleration field. And then one more derivative of that gives you the mass density. So we decided to just try this out on the Gaia data. Well, first we tried it out on some hydrodynamical simulations, and we got a good result. So then we tried it on the Gaia data, and if this were to work, it would give you a completely non-parametric model and symmetry-free, fully data-driven determination of the local dark matter density in full 3D. Okay, so these are the results we got for the acceleration field along different, projected along different arcs. So our data set, we were able to look at basically plus or minus, so a 3 or so kiloparsec ball around where we are. And so these are the green and the orange curves are shown, and the purple curves are shown here, acceleration, the components of the 3D acceleration vector versus different directions. And so one interesting thing is we can test, for instance, you expect there to be like a north-south symmetry, or approximately, or an azimuthal symmetry based on dynamical equilibrium. And we didn't assume that, so we could test that. We could see, if we close on that assumption. And we find pretty good closure to within, I would say, 10% in the various directions we looked. We can also compare our acceleration determination at the solar location directly to a Gaia determination. Gaia uses a completely different technique, the aberration of a distant quasar, distant quasars. And yeah, the agreement is within, within a couple of sigma, so pretty good agreement, I would say. This is the real, I think, money plot for us, is the mass density as a function of how far off the disk you are going through the solar location. So this gray curve is the total mass density. Each data point here is inferred from the data, fully data-driven, and is an independent measurement of the total mass density at that location. And this is for 3 different arcs that pierce through the disk, okay? And so assuming spherical symmetry, after you subtract off the stars and the gas, this should just be a constant. And what we see is pretty consistent with a constant, and that's the spherically symmetric dark matter density. So yeah, the residuals of this is what's left is the dark matter density, and our value that we get at the solar radius is consistent with previous measurements, a bit on the high side, 0.47 in particle physics units, but pretty consistent, I would say, with the previous measurements, hopefully with more realistic error bars. So I think with that, I think I will just end. We've also applied techniques to search for stellar streams, but I think I'm out of time. So let me just finish with conclusions. Yeah, I think as we go from proof of concept to deployment on data, things like the issue of domain adaptation becomes increasingly relevant. There's lots of different techniques that are being explored and tested out. I don't think any single one of them is, a magic bullet, but we're going to need a diverse toolbox for all the different kinds of domain shift and all the different kinds of situations we're going to find ourselves in. I would say doing domain adaptation for SBI is an interesting future direction. Some things I didn't really talk about in the talk are also worth discussing maybe is the connection to uncertainty quantification. So ideally you want to mitigate, this is what we talked about already, ideally you want to mitigate the domain shift and to quantify it, or what's left. And that remaining domain shift is then a source of systematic uncertainty. And lastly, I don't know how much this comes up in Astro, but in high energy physics, often to mitigate domain shift, we use control regions. So regions in the data phase space where we know something about the data, we know the labels or something, and we could use that to pin down the difference between the model and the data. I'm not sure I've seen analogs of that in astronomy, but I'd be interested to know if anything like that exists. So yeah. All right, thanks for listening to me for like an hour.
Okay, we are out of time, but are there any more quick questions in the room? Yeah, go ahead.
This last part was super interesting because it's, I mean, that this local dark matter density has been really hard to measure.
Yeah.
What do you really mean by model free?
Good. So, okay, so we make one key assumption, which you might disagree with, which is this assumption of local, of dynamic equilibrium of the tracer stars. But after that, the model is the normalizing flow. And I also struggled with this, but I made my peace. So for a long time, I criticized ML people for saying that these neural networks are non-parametric, because in fact, they're very parametric. They have like a billion parameters or whatever. So how does that become non-parametric? So I made my peace with that. So they're non-parametric in the sense that, I don't know, like a pile of sand is not really individual sand grains anymore. It's some collective behavior of the weights that's going on here. So in that sense, the normalizing flow is the model, but it's so flexible. It has so many parameters that it's really, it's a model. It's a data-driven model, I would say, for the phase space density. So, as opposed to many of the other approaches which try to fit the potential or the acceleration field to a parametric model, everything after we've learned this is like derived. So we don't assume anything about the form of A or anything like that.
And you're not assuming it's isotropic.
We're not assuming it's isotropic.
Space or something.
Yeah, a lot of these other previous approaches had to make assumptions like that because they were binning the data. So they had to basically augment the data by integrating over the phi direction or something like that. Yeah.
Okay, cool.
Mm-hmm.
Yeah.
Any other quick questions? Anything on Slack?
Something back there, yeah.
Oh, okay, go ahead.
Yeah, just a quick question on the plot of the density. I'm curious, how do you model the dust?
Good.
Gas? Yeah.
Good. So indeed, that's why in this first work here on the Gaia data, we ran the method on the full ball centered around us, and then so that learns the observed phase space density, but that, of course, that is convolved with the dust occlusion. So it's not the phase space density we're really after. So these arcs that I drew here were an attempt to find like lanes through the data set that were not occluded by dust. And so here's where we really think we have a reliable measurement. Currently, we have a technique that's going to hopefully come out soon where we're improving on all of this, we can also learn the dust at the same time. So yeah, so basically, at the risk of giving too much away, I guess, we found a technique where basically you model the observed phase space density as the true one, which should obey the Boltzmann equation, times some dust factor, which is like an efficiency factor. And if you work out the math of that, you could actually learn simultaneously the acceleration field and this dust efficiency field. So we get like a dust map and the true acceleration and everything throughout the whole ball now. So yeah, that'll be coming out soon.
Thanks.
Okay, so we have a break, right? So maybe we could continue the discussion during coffee and then come back afterwards for one more pre-recorded talk. So let's thank the speaker one more time.